Okay, let's go. First things first. Problem sets got back today. Overall, I was pretty pleased. This is about quality work and making sure that you're showing me how you're getting everything, and that you guys did a pretty good job on that. Okay, so keep that up. The way the problem sets work is each week you'll get problems that can come from anywhere. So don't be surprised if, 2 months from now you see a limit problem. Okay, because that's how this is going to work. Hi. And I'll trade you. Okay, next one's due next Tuesday, and we move on. All right, let's go to the board. These were a couple of the major problems from page 78. So, what on earth is going on here? So, number 12, we're asked to find the limit as x approaches 2 from the right of this goofy thing. It's the absolute value of x minus 2 over x minus 2. So, yesterday, remember, we created that process, how to attack any limit problem. So, you see if you can plug it in. No, you get 0 over 0. That's no good. This one's maybe kind of hard to visualize. Okay, so that maybe that's not so good. Can you cancel anything on this? So if you cancel this and you cancel this, then you get this. The limit as x approaches 2 to the right of the absolute value. Right? Because it cancels? No, so that's no good. But what's weird is it's the same thing in the top and the bottom. Okay, now stop and think about that. It's the same thing in the top and the bottom. The top one just happens to be absolute value. Okay? We know that if it's the same thing on the top and the bottom, the answer is 1, right? So this one has something to do with 1. So watch what happens here. I'm going to take that function. I'm just going to play with it a little bit. I'm going to plug in some numbers. What if we plug in a number that's to the right of 3, or to the right of the 2? So I plug in a 3. I get the absolute value of 1 divided by 1, which is 1. Okay. What if I pick one that's really close to 2? So 2.1, that's to the right. So it's 2.1 minus 2, absolute value, over 2.1 minus 2. You get 0.1 over 0.1, which is 1. So it turns out that if you're to the right of 2, the answer is always 1. And then if you're to the left of 2, it's always negative 1, because you end up subtracting, you get a negative on the top, but on the bottom, but the numerator is always positive. For example, look at the back, look at the front board. I've graphed it. Here is the absolute value of x minus 2 divided by x minus 2. So look at, this is the graph of it. Okay, so it's 1, always 1 to the right. It's always negative 1 to the left of the x equals 2. What happens when it's exactly x equals 2? Yeah, so what does the graph look like? What happens at exactly x equals 2? Asymptote? Wait a second, you can cancel. What did that mean when they could cancel? It's a hole. And what happens here is this is the graph. That's what the actual graph looks like. Okay? It's always 1 coming from the right. It's always left. It's always negative 1 coming from the left. And there is no value. There is no functional value. So at x equals 2. So the answer to that, what is the limit as x approaches 2 from the right? That answer is 1. Kendra, your problem set's on the front table. Okay, 16 is a really good question. It says, what is the limit as x approaches 2 of the function, where the function is this big glob here? Okay, it's a piecewise function, and lo and behold, would you imagine that it splits off where x is equal to 2. Okay? That's the left and the right half of it. So now stop and think. Okay? Actually, these are really good words to live by. Okay? Whenever you're doing a problem you don't understand, just stop and think. Okay, what do I got? Well, this is a piecewise function that separates at x equals 2. And I spy it's 2 parabolas. Okay? So here's what I know. To the left of 2, okay, that's x is less than 2, it's this parabola. Now I don't know what that parabola looks like, but I know that it's facing upward. So I don't know, I'll just draw a random facing upward parabola. Okay? It's got to have a hole at x, oops, wrong spot, at x equals 2. Okay? And then I see another parabola to the right that we graphed when x is greater than or equal to 2, and it's facing downward. So again, I don't know what it looks like. Now, it could look like this, right? This graph could be below or it could be up above, or it could connect right on the money. Okay? How can we determine whether or not it connects right on the money? We plug it in. So we're going to plug in the 2 into both of the equations and see what we get. So in the first one, all right, watch my math here. In the first one, it's 2 squared minus 4 times 2 plus 6. 4 minus a is negative 4 plus 6. Did you get an answer of 2? I'm going to check my math here. Here it's negative 2 squared plus 4 times 2 minus 2. It's negative 4, negative 6 plus 8. That's 2. I got the same answer for both. Now stop and think what that means. That means when x is equal to 2, these two graphs actually perfectly connect, even though they're two different parabolas. See that? So that means if I want to know what is the limit as x is approaching 2, that means that the left-hand limit is going to equal the right-hand limit, and it's going to be whatever that functional value was. And in this case, it was x equals 2. So the answer is 2. It's this 2, not that 2. Make sense? Okay. Next one. That goofy symbol there, that's the greatest integer function, or the step function. Okay, so we're approaching 4 from the left. So stop and think. If I'm going to approach 4 from the left, 1, 2, 3, 4, that means I'm going to plug in numbers just to the left of 4. So if I plug in a 3, I get a number. So I'm going to plug in 3. F of 3 is equal to 3 times the greatest integer function value of 3 minus 5, which is 3 times 3 minus 5, which is 4. Well, that's close, but it's not close enough. I'm going to go 3.9. So that gives me 3 times the greatest integer function value of 3.9 minus 5. Well, this is 3. What's the greatest integer function value of 3.9? 3 minus 5, and it's still 4. That means for this thing right here, as I approach here, as I approach x equals 4, I'm getting an answer of 4. 1, 2, 3, 4. And as I go to the left, this is what it looks like. This is what I know that it looks like to the left of this. So the limit as x approaches 4 of this thing is 4, the y value. That make sense? Okay. Lots of different situations. This is like that neural network talk that we were talking about. You see, it's so important to see a wide variety of problems so that you can build your network to handle anything that comes your way. All right, this says verify the intermediate value theorem for this thing. We have a function, we've got an interval, and we have an f of c value. Okay, so watch the picture here. My interval is 0 to 5. 1, 2, 3, 4, 5. Okay, so we had to have a closed interval for intermediate value theorem. We had to have a continuous function, okay, which that's just a parabola, so I know it's continuous on the interval. And then we have this value here. Well, so what I'm going to do is I'm going to plug in the x equals 0 and get my answer. So I plug in f of 0, and I get -1. So I'll plot this right here. This is at -1. And then I'm going to find f of 5. Okay, what do I got here? 25 plus 5 minus 1, that's 29. So my scale's a little bit weird, but that's okay. When x is 5, I'm at 29. So this is a parabola that's facing upward, so I know the graph looks like this some way. Okay? I know it's got to look like that in some way. It's got to go from there to there. The intermediate value theorem said this. If you have a continuous function on an interval, then you can pick any value on the y. So 11 is like over here somewhere. If you pick a value over here, then there has to be a c value for which f of c is equal to 11. In this case, if you bring this all the way across here, on my graph, it looks like c would be somewhere around here. That's the graphical representation of what the mean value theorem says. Pick a y value, there has to be an x value that matches it, if the function's continuous. Well, this validates it from a visual standpoint, but it doesn't from an algebraic standpoint, so let's prove it algebraically. It says this: at some point, x squared plus x minus 1 has to equal 11. That's what it says has to happen. At some point, the function has to equal 11. Okay, so we just solve. So solve this bugger. We got x squared plus x minus 12 is equal to 0. And factor and solve x, 3, 4. And this is going to be a minus and a plus. Therefore, x equals 3 and -4. So my graph is a little bit off here. The c value is 3, such that if we were to plug 3 into the function, we should get 11. F of 3 is equal to 3 squared plus 3 minus 1, which is 11. Make sense? Here's a weird application of the intermediate value theorem. Look at this. It actually has to do with something like your height. Okay? So picture this. This is an alternative explanation of the intermediate value theorem. When you were born, that's x equals 0, or t equals 0, whatever. Let's pretend, just for the sake of it, you were 18 inches long. Isn't that weird? You're called long when you're a kid, but then you're tall. Why don't they call you tall? Maybe it's because they laid you down. I don't know. So 1, 2, 1, 2. So this is 1.5. So this is you when you were born. Okay? And then this is you now. Let's suppose you're 17. And this is how many feet? 1, 2, 3, 4, 5. Let's pretend you're 6 foot tall right now. Sorry, Amy. Off by a foot. 1, 2, 3. Oh, yeah, there, yeah. Okay? Most people's growth patterns look like this. Okay? You grow a lot early on. Here's the intermediate value theorem. Intermediate value theorem says if you have a continuous function, if this is your height, okay, this is height in feet, okay, is your height a continuous function? At every given moment of your time that you are alive, are you a certain height? If you're not, we have to have a talk. Okay? So you are always a height. That means your height is a function of time. I'm not going to answer you. Now, intermediate value says, hey, if at some point in your lifetime, or you were 1.5 foot, and then another time later on you were 6 feet, then that has to mean at some point you had to be exactly 4 feet tall. That's what it's... Something important. Hello. Oh. Whatever. So that's what this is saying. Okay? At some point in your life, you had to be exactly 4 feet tall. No question about it. Even if you grew and you shrunk, which is what happens like when you get older, you know. Okay? You have to be that particular height because your height is continuous. Does that make sense? Okay. All right. Set that aside. We'll open up your notebook. We're going to do our topic today, which is limits to infinity. No. Now we're on 3 point something. 3.5. Oh, am I? Yeah. All right, so today's lesson is again something that we've touched on and you actually covered last year, so we can go through this quickly. 3.5, this is limits at infinity. And what the goal here is to find limits where x is approaching infinity or x is approaching negative infinity. That's the difference between yesterday's lesson and this one. Okay? All right. I'm going to try to demo this with the graphs here. Oh, I'm going to make a note here as well. We are looking at the end behavior of a function. That's kind of a key phrase here. We're looking at the end behavior. What happens at the ends? Meaning really positive or really negative. What happens there? Okay, first one we'll start off with is what is the limit as x is approaching infinity of 10x plus 2 over x minus 3. 10x plus 2 over x minus 3. the limit as x is approaching infinity. Ten? Did 10, anybody else get 10? Okay, how'd you get 10? 10 is the correct answer.
The coefficients of the x's.
Yeah, you may have remembered something from last year where you studied the coefficients of the terms. This answer is 10. This is x to the first, this is x to the first. It's the highest degree for each one of those. Last year you learned, oh, the answer to this is 10 over 1, where we just look at those and the answer is 10. Remember something like that? Yes. It has to do with asymptotes. Now, watch this. I have this graph right here. Okay? This is the graph of the function. Okay? So now look carefully at this. This graph is a hyperbola. It's the graph of this function right here. Okay? What we want to focus on is what's happening as x is going towards infinity. Okay, what's happening to the y value? It's going towards 10. Okay? If you were to make a table and just kind of punch in numbers, take that function, find f of 10, f of 100, f of 1,000, f of 10,000. What you'd notice is we'd be taking, let's do the 10,000. 10 times 10,000 plus 2 divided by 10,000 minus 3. Okay, so 10 times 10,000, that's 100,000 divided by 10,000, which is 10. These numbers here end up being not really that important, especially when we're talking infinity, because infinity is crazy big. Okay, so as we approach infinity, that's why the graph has an asymptote at x equals 10. Now watch this. We can modify this in different ways. What if I put this as 10 over 2? See where the asymptote is? Or what if I make this negative 1? You look really close. Where's the asymptote? Negative 0.5. See? Negative 1 over 2. That's where the asymptote is. It's at negative 0.5. Okay? So, when the exponents are when the numerator grows at the same rate as the denominator, then all you have to do is take a look at the coefficients. Okay? All right. Next one. Well, I'll demo this with this one right here. Check this graph out. X squared plus x minus 1 divided by x squared minus x plus 1. What would you say the what is the limit as x approaches infinity? 1. Now look at, there's an asymptote here, but it does do this little squiggle thing. The limit is still 1. Okay? But it doesn't have the asymptote like the other one does, because this is here. But we don't care about this, because we're talking about end behavior. What happens at the ends, not what happens in the middle. We don't care about that. All right, next one. So when the coefficients are the same, that means both the numerator and denominator are growing at the same rate. Okay, let's do another one. Let's do the limit as x is approaching infinity of 5x minus 3 over x squared plus 4. 5x minus 3 divided by x squared plus 4. Okay, what's the answer? 0. Okay, if I go out far enough on this thing, you'll see that as I approach infinity, this is getting closer and closer to 0. Okay, why is that? Why is the answer to this limit 0? The denominator is growing faster than the numerator. Anytime you have that, you're going to have an answer of 0. Now watch this, it's pretty funny. Even if you put a really big number in here, like what if I put in 500, 5,000, okay? You're thinking, well, there's no way that's going to turn out, but look at what happens. Okay? That 500, even that 5,000, even though it's really big, doesn't stand a chance against the x squared. Because as you plug in larger and larger numbers, this whole fraction is going to get closer and closer to 0. Doesn't stand a chance. Okay. So, and notice that it doesn't matter what exponent. If I put a 3 in here, it just makes it go faster to 0. Okay. So when the denominator is growing faster than the numerator, the answer is always 0. So what's the last case? The numerator growing faster than the denominator. So an example of that, limit as x approaches infinity of, say, x cubed plus or minus 9 over x minus 4. The key here is only just the leading term's coefficient. What do you think the answer to this one is? Got an answer? As x approaches infinity. Can you see to the right here? This one's kind of hard to tell. I'm going to shrink that to 2. Okay. What's going on here is as x is approaching infinity, this thing it's going upward. So the answer is positive infinity for this particular one. It doesn't mean that the answer is always positive infinity. It could be negative infinity as well. Let me show you an example there. So, this is a graph where the denominator is growing slower than the numerator. And the end result is that you end up with a negative answer as you let x get larger and larger. Stop and think about it. Pick a number like 1,000. Take 1,000, square it, then take the opposite of it. That's a negative million. Minus 9, and then divide it by a positive number. 1,000 minus 4. So negative divided by a positive. Okay. So the sign of the answer that you get here determines whether or not your answer here is positive or negative. Just ringing a bell from last year with asymptotes. Last year you would have talked about y equals 0 as an asymptote, y equals some number as an asymptote, or you would have called it a slant asymptote. Okay, this is an example of a slant asymptote because as x is getting bigger, the final answer is it's not approaching 0 or a specific number. Okay, let me look at this one. Let me give it here. What about this? What is the limit as x is approaching infinity of x squared over e to the x? Different kind of problem. What is the answer as limit as x approaches infinity? I'm hearing 0. Anybody else think 0? Remember what I said? If the denominator is growing faster than the numerator, then the answer is 0. This is a case of that. And that I want to try to get away from just saying, oh, just look at, these are polynomials. We don't always have to have polynomials. Okay? We can have weird things that look like this. This is e to the x down here. And that, let's make this a function, I guess. Oh, I'm so far away. That's why. So at some point when we get in here, we should see something a little different. There I got a little wiggle. Phew. Okay. So what happens between 0 and 4 is the most dramatic between those. The key here is that the denominator is growing faster as x is approaching infinity. So therefore the answer is 0. What is the answer as the limit, that same function, the limit as x approaches negative infinity? It's positive infinity. Look at the graph. Okay? The graph is going up, but if I zoom out, you'll see that it goes up, 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 up. It's never coming down. Without the graph, look at this right here. When x is a negative number, you're taking e to a negative number, which reciprocates it. It makes it 1 over, which makes it a smaller number. So that's why the graph of this, you're taking a big number divided by a really super small number, and that's why it ends up being positive. All right. Give you another one. Yes?
What happens when you have like an x squared under square root sign?
I was just going to do that. So, next one. Limit as x approaches infinity of, let's do an x squared over the square root of x. Okay? So, x squared divided by square root of x. So it's the orange one here. Zooming out, looks like what's the answer? Infinity is correct. Why is that? What's the exponent on the bottom? 1/2. Okay? So when we say, who's growing faster? Top is growing faster. Therefore, we have to look at the end result. Is it a positive number or is it a negative number? In this case, it's a positive number. That's why the answer is positive infinity. Yeah.
If you have like a polynomial that has x squared plus x plus 1 under square root, do you only need to take
The leading
base?
term. The leading term. So if I had a weird one, actually, we can take one that's over there. Let's do this one right here, and I'll just take this and I'll say square root of x. Okay, and draw that one. Yeah.
Yeah, but if the x, the top term would be in the bottom term.
Oh, so flip them? So let's do this one here. So it's the blue one.
I mean, like, square root is still in the denominator, but the x squared is under the square root with the rest of the polynomial. Yes.
Like what?
So like x over the square root of the polynomial.
Oh, okay, let's try this. Like that? Okay, so we're taking the x squared here. What's the end result of the denominator? Look carefully. What's the end result of how fast the bottom is growing if it's the square root of an x squared plus x minus 1? It's just x, okay? What happens here is you take the leading term, this is the one that's got the most power, and you can take the square root of the x squared, which is just x. So this one is the same as this first one, because both the top and the bottom are growing at the same rate. Okay, that's a really good question. Watch this. Let me get rid of this guy here. If I put a 5 here, it's 5x over the square root of this. Do you see that the limit is 5? Okay, and that's because this x squared, we're taking the square root of it, so it has a growth rate of just x. See that? Okay, so for every single one of these problems, you just have to think, all right, look at the numerator, look at the denominator, who's growing faster, make your decision based upon that, and then watch for positives and negatives. Okay, and whether or not it's going up or it's going down as you look at each one of those. Yes.
So in this section, you still want to say like chapter summary?
Yes. This section 3.5 still goes in the chapter summary with this grouping, because it all has to do with limits.
What does the problem solving include as a assignment?
Yeah, say it again.
Was it problem solving?
Oh, and the problem solving, that's an optional question.
What is the chapter summary?
Chapter summary will be due on the day of the test, which I can see happening maybe like next Friday. We'll solidify that for sure next week. Next week, Friday. I will never, ever, ever have a test immediately after we cover something. I need to wait really long just to see if you really remember it.
Yeah, oh, that's.
I swear.
The test is testing. Actually,
Yeah, I'll get you a copy of that.
Yeah, I will.
Yeah. Okay.
Hard to say off.
Watch out, your pencils are about ready to fall out.
This is my only pencil right now.
I can't remember which arm is my good arm.
I'm going to get one after school.
your water along, okay.
No.